Now, it's quite interesting because like quadratic equations, cubic equations also have different natures of roots. So for cubic equations, there are 3 distinct real roots because now it's x cubed. So there are 3 distinct real roots. There can be 2 equal real roots and 1 distinct real root, 3 equal real roots, 1 real root, and 2 non-real root. What does non-real root mean? Basically, they are not real numbers. These are the different permutations of the possible roots, and it comes with possible cubic equation curves. So similarly to quadratic equations, roots of cubic equations are the x-coordinates of points of intersection with the x-axis. Oops. Okay, this is not straight line. So, if let's say for example, your root is 1, then your curve must cut the x-axis at 1. Cut means touch or pass or go through. It depends on the nature of your equation. So in general, this is a general case. You don't really have to know how to sketch the x-intercept and whatever at this point in time. But if let's say, in general, if this is your cubic equation, for a is greater than 0, your cubic curve goes down and then up first. So it goes down first and then up. And then for a smaller than 0, it goes up first and then down. But then for the x-intercepts and y-intercepts, you will have to see the actual cubic equation. Now, cubic identities, much like quadratic identities, a squared plus 2ab plus b squared equals to bracket a plus b close bracket square, cubic identities are also something like that. But take note that there's no 2 inside. Don't mix it up with quadratics. Yeah, these are just the 2. Just remember them. Now partial fractions, which is the last part of our going through. So partial fractions, they are only for proper fractions, but later I'll teach you how to find out how to find with improper fractions. So we all know from primary school and all that this is only proper when the degree of p is smaller than degree of q, right? Because if let's say this is like that, then it's not proper because it just equals to x. But if let's say it's x over x squared, you can't really, it just becomes 1 over x, which is a proper fraction. So there are many cases of partial fractions. Instead of adding fractions together, which is like half plus 1/3 equals to something, last time we used to find out what's this. Now we're given this, and then we're supposed to find out what are these two. So it's the reverse. So there are many cases. So case 1 for partial fraction is that proper fraction with distinct linear factors in denominator. So case 1 is for proper fractions with distinct linear factors. So the denominator of the right hand side is the product of the denominators of the fractions on the left hand side, where both fractions on left hand side and right hand side are proper. So what I talked about just now is this. So basically it's distinct linear factors in the denominator, and it's a proper fraction because the highest degree is in the denominator, that being x squared. When you see these kinds of improper fractions, use this kind of like formula. So if you notice, ax plus b goes here, cx plus d goes here, and a and b are constant. So basically you have to find out what are a and b. One example, very straightforward. When they ask you to find the solving for partial fractions, right, of this, immediately you can see you split this up, and then you immediately multiply throughout by this to get rid of the denominator. Because when you multiply, to get rid of the denominator, and then from here you either let x be different values, or like rather that means substitute suitable values of x, like let x equals to -1, let x equals to -2, etc., or you equate and compare coefficients. You can also do it by observation. So next, case 2 is proper fractions with repeated linear factors in the denominator. So the denominator of right hand side is denominator of left hand side with the higher degree. So when you see this, which is basically repeated linear factors because of the square, you immediately must know to separate it this way. So one must be ax plus b, which is the same as this. The other one must have the square. And then you solve it like what I kind of told you just now in case 1. Next, case 3. So case 3 is the proper fraction with quadratic factor x squared plus c squared in the denominator. And this x squared plus c squared cannot be factorized. So how are you going to split it? Basically, denominator of the right hand side is product of denominator of left hand side. This cannot be factorized, so you immediately must know how to split the fraction into this. And c in this case is already given to you in the question, so it's just any positive number. So where, remember that bx plus c, so this is where a, b, and c are constants, and then you solve from there as well. Now for partial fractions, for improper algebraic fractions, there are certain steps that you can follow to find out the partial fractions of those. Firstly, check whether the fraction is proper or improper. If it's proper, then you can use the one of the 3 cases that I taught you just now. If it's improper, perform long division, and then you express the whole thing in division algorithm, which is what we've talked about just now, and then divide through the divisor and solve for a, b, and or c using either case 1, 2, or 3 depending on the factors in denominator. So for example, you get an improper fraction already, and then you divide through the divisor, and then after that you get another thingy. So you divide through, which gives you the dividend equals to divisor times quotient plus remainder, and then you take the quotient and then solve using either case 1, 2, or 3, and then after that for the final answer you basically take the solved already quotient, which is like these, like the 2 fractions, and then you add it into the division algorithm, replacing the quotient. Let me check the contents page to see if I've covered everything. Yes, I have, and thank you for watching today, and I hope you will tune in to the next video soon. Bye!